welcome back to the channel. In today's video, we are going to take a deep dive into an interesting physics problems from geometrical optics that will help you sharpen your problem solving skills and strengthen your fundamentals. So I will walk you through the concept step by step and explain the logic behind each move and also point out the common mistakes students usually make. So grab your notebook, stay focused, and let's crack the problems together. So in the previous video, someone requested to take up problems from geometrical optics. So yeah, today I came up with 3 problems from geometrical optics. So yeah, let's continue. So the first problem says we have the figure shows a device used to measure small twist in a thread. A plane mirror is suspended from a twist-free thread. A light ray striking the mirror is reflected onto a screen placed at a distance d equals 1 meter from the mirror. So as the thread is twisted by an angle theta, so the mirror rotates by an angle theta. The light spot on the screen moves from A to B such that AB equals 0.5 centimeter. Find the angle theta. So as the source gives light, so it strikes on the mirror, so that the thread moves by a small angle theta. So we have to find that angle theta. Okay, so the after reflection it falls on the screen and it moves from A to B. Okay, so before solving the problem, we have to know this property. As the mirror rotates with the angle theta, so that reflected ray rotates by an angle 2 theta. So I think you all know this property. So let's continue the solution. So using this property, I drawn this diagram. So as the mirror rotates by an angle theta, so the reflected ray rotates by an angle 2 theta. Okay, so in the question they have given AB distance. So this is the arc length, and D we can assume that is radius. So angle equals arc length upon radius. From this we can directly find out the angle theta, that equals 0.14 degrees. So this is a pretty easy problem. So yeah, so the second problem says on a hot summer day in a desert, the refractive index of atmosphere changes with height y above the surface of the earth as mu equals mu naught times 1 plus by whole power 1 by 2, where mu naught is the refractive index at the surface and b equals 6 into 10 power minus 4 meter inverse. A man of height 1.5 meters is standing on a straight level road. Calculate the distance beyond which he cannot see the point on the road. Okay, so this is a standard problems based on variable refractive index. So you can blindly follow this method as a given. So yeah, as the light enters the atmosphere at a grazing incidence 90 degrees, so it takes a parabolic curve path. So here we consider a parallel slab, as every point in on this slab the y coordinate is same. As the y coordinate increases, refractive index also increases, as they have mentioned in the question. So we have drawn normal here, and this is the angle of incidence we know. So I have drawn here a tangent to know the slope. Okay, so yeah, I have simply used Snell's law here and here, as we studied this property in the composite slabs. So mu naught sin 90 equals mu times sin I. From this sin I equals 1 by 1 plus by whole power 1 by 2. We assume this equation as equation 1. So now we write slope. We have studied this property in tangents and normals in class 11th calculus. Tan theta equals dy by dx. So basically here dy by dx is the slope. So in this diagram, slope is 90 minus I. So we simply substitute theta as 90 minus I. So tan 90 minus I equals dy by dx. So cot I equals dy by dx. We assume this as equation 2. From 1, we simply consider a right angle triangle and find out the value of cot I. So after finding the value of cot I equals root of by. So from equation 2 and 3, we can simply equate dy by dx equals root by. After integrating both sides from 0 to h and 0 to x, we can find the value of x equals 2 times root of h upon b. So after substituting the values, that we got x equals 100 meters. So we have to find the distance beyond which he cannot see a point on the road. So we basically find it here, the distance x, so that a man cannot see the point on the road. Okay, So yeah, coming to the third problem, we have a convex lens of a focal length 20 centimeters and another plano convex lens of focal length 40 centimeters are placed coaxially. The plane surface of the plano convex lens is silvered and an object O is kept on the principal axis at a distance 10 centimeters from the convex lens. Find the distance d between two lenses so that final image is formed on the object itself. So in the problem, we have a convex lens and a plano convex lens. One side is silvered. Okay. So we have kept the object at a 10 centimeters from convex lens. So after refraction, so the image finally forms on the object itself. They have mentioned. So we have to find the distance d between two lenses. Okay. So in the question they have given f1 equals 20 centimeters and f2 equals 40 centimeters. So we solve this problem step by step carefully. So first we write equations for convex lens. So for convex lens they have given u equals minus 10 centimeters, basically object distance. So I used here lens law, 1 by f1 equals 1 by v minus 1 by u. So you know sign conventions, right? So focal length equals positive 20 centimeters and object distance we know minus 10 centimeters. Basically it is the left side of the lens. Okay, here we assume negative and here positive. Okay, yeah, after calculating we got image distance as minus 20 centimeters. So it is the image distance for convex lens. So yeah, this is 20 centimeters. So this image will act as an object for this plano convex lens. Okay, this is the main property here we use. Okay, so for object distance for plano convex lens d plus 20 centimeters. So we simply use lens maker formula. So for lens maker formula 1 by f2 equals mu minus 1 times 1 by r of r1 minus 1 by r2. Here r1 is capital R for convex lens and minus r2 is for plane mirror. The radius of curvature is infinite. Okay, so from this we have got 1 by 40 equals mu minus 1 by capital R. We assume this as equation 2. Here mu is the refractive index of this plano convex lens and outside we assume as 1. Okay, air basically. So now we use refraction formula for this curved surface. Okay, yeah, mu2 upon v2 minus mu1 upon u, that equals mu2 minus mu1 upon r. This is basically formula. This is, yeah. Now we substitute v2 as infinite. Why infinite means, so as the ray falls on the mirror, it incidents normally on the mirror so that it retraces the path and finally image forms on the object itself. Okay, we know basically as the light falls normally it retraces the path backside. Okay, yeah. We substitute v2 as infinite and mu2 as mu, and mu1 we assume as 1 and u equals minus of d plus 20 centimeters. Yeah, after doing calculation we have finally got d equals 20 meters. So that's it for today, guys. If you have any doubts, comment in the comment box. So thanks for watching and keep subscribe and do like. Yeah.